It occurred to me as I woke up this morning that today or tomorrow or the next day, but sometime in this week, somewhere in America, a mom and dad will have a new baby and they will get a diagnosis of KCNQ2. We know that 140 children a year in the United States, approximately, are born with KCNQ2. So there is a new mom, a new dad, grandparents, siblings. Who knows that family, but we know what they're about to hit and what that's going to mean. And what we are doing here together, all meeting, will change their lives. It all began, this particular piece of it, in Europe in a research lab, because we knew about KCNQ2, but this particular way in which it had a nastier side than we knew was the result of some research done by the woman you're about to meet. Sarah Wekhuizen, whose name I said wrong. Can I say that again? Sarah Wekhuizen, who's currently at the University of Antwerp in Belgium, is a researcher. She's a neurologist. She's passionate about the hunt, about tracking down and understanding and decoding these rare epilepsies and understanding what they mean. And it's by that first step that we have an answer to what. And then we can figure out all the other pieces, how we deal with it, the way in which it unfolds. But if we don't know that piece from that lab, from doctors like Sarah, then we can't start. So it is with great pleasure that I introduce you to Sarah Wekhuizen.
Thank you, Sarah, for the beautiful introduction. I'm very pleased to be here for the third time, and it's incredible to see how the audience has grown over the last 3 years, and I'm sure next year it will be even bigger. And today I was asked to talk about the topic KCNQ2, the global perspective, and I think they gave it to me because I'm not from the US, as you might hear. I'm from Europe, so I see it a little bit from the other side of the ocean. Because first of all, KCNQ2 is a worldwide disease, of course. And we know, and we've talked about it yesterday too, that it's most of the more severe cases, which we call KCNQ2 encephalopathy, it's caused by a de novo mutation, which means that it happens or it occurs suddenly during the development of the embryo. And of course, this is a chance thing, and chance happens all over the world. So there's no reason to think that it would be more common here in the US than it would be anywhere else. And we're sure there's kids out there everywhere. And I asked Jim for an overview of the parents and children that are in the KCNQ2 Cure organization, and that's what he gave me. So almost half of them are from outside of the USA, and a few of them are here. There's people from Germany, from Norway, from El Salvador, I understand. There's even people in there from the Middle East, from Asia. So it's great to see that the organization is expanding beyond the borders. The same is happening, I think, when you look at what researchers do and clinicians all over the world. I just listed up the bigger reports in literature, so in medical literature, so reports or groups that published larger groups of patients. Most of them come from Europe, often in collaboration with the Australians, and that's Ingrid Scheffer's group. And this is not because patients are more common there, it's just because in Europe you have a tradition of phenotyping and of describing patients a bit more than elsewhere or than in the USA. The recent paper on ezogabine treatment came from the description of patients from the USA, but there's more papers on the way, and this is largely due to the efforts of a lot of these people here. Under influence of the patient organization, I think, we learned to work together, to put our heads together, and to put information together, and it's leading to a very fruitful collaboration, I think. So what we what we did and what we still do is it's teamwork, and that allows us to go forward quicker than we would do when we work alone. And the last, I think 4 years now, we already learned quite a lot. I think you've seen more or less this slide yesterday from Peter. We know now that KCNQ2 related disorders, it's a spectrum, and that's what you see here today also when you look around and you look at all these kids. There's very severely affected kids, there are more mildly affected kids, and then the ones that we probably do not see here are the ones that are developed totally normal, the ones that we call benign familial neonatal epilepsy, which are often in families. And we know in the meantime that what determines this outcome, it's largely an effect of the individual variant that patients carry. And of course, there's always a genetic background. There might be some children here that carry exactly the same variants, but still they're different. And that's because we're all different. We all have our own genetic constitution. This, by the way, also relates to the drug response. And there were some remarks yesterday that everybody here is on a different drug and they react differently. We know from other epilepsy that the genetic background also has an influence on that. So the reason why one responds to Keppra and not the other one doesn't, it might also have to do with the genetic background rather than this KCNQ2 variant. And then probably the seizure severity and the duration of the seizures, it might also play some kind of role. We might expect that when you have very severe and very frequent seizures that you do less well, although it's very difficult to prove in this entity. As said, and as we know, the benign forms, they're often inherited, so you pass it on to your children. Moms have neonatal seizures, and then their son and daughters have neonatal seizures, and so on and so on. And then at the more severe end, most of these mutations occur de novo. So mom and dad are perfectly healthy, and then suddenly there's this child that is not that healthy and presents problems. We know that there is a few exceptions, and that's parental mosaicism, and I will come back to that later. This is a case where mom or dad, they're healthy, or maybe they might have neonatal seizures, but they develop perfectly well. But then they have a kid that's very severely affected, and this is, we have shown now that some of these parents carry this severe variant, but only in a part of their body cells. We have studied these variants, or people here in the audience, like Ed has studied a lot of them. And we know that the benign variants in general, they cause less than 50% reduction in this M current. And the M current, that's the current that goes through this potassium channel that's encoded by this gene. And then at the severe end, most of these variants cause more than 50% of M current reduction, though. So it functions even less well. There's a few exceptions, and that's something from the last year or maybe 2 years. In the meantime, there's a few exceptions of mutations or variants that cause an increase in the M current. So these channels are open too much, and I was one of the parents yesterday that made that told us that his child carries one of these variants. So that's what we call a gain of function. So we understand more or less what these variants do. There's some knowledge about the treatment, or we have some ideas. There's some reports on children that responded well to sodium channel blockers, and those are drugs like carbamazepine. And there's even this one paper, somebody yesterday showed it, that shows that many of these children respond well to these sodium channel blockers, mostly when it comes to seizures. So the effect on development, it's less clear. But at least we have an idea what to try first. And then there's retigabine, ezogabine, potiga, as many of you know. It comes from the idea that we know that many of these variants call a loss of function, so a reduction of this M current. And we know that retigabine, ezogabine opens the channel more, so at least it started in a dish. And then it was shown that many of these variants, if you if you add ezogabine or retigabine to it, that the channel opens more, so you can revert the effect. I said it started in a dish, and then we tried it in patients. It started with one patient in one particular paper, and then John here, together with Ed, they have this nice study of 11 patients that tried retigabine and ezogabine. Some of them responded well with a reduction in the seizure frequency. Again, the effect on development is less clear, and this is something that probably many of you can comment on. Some might have the impression that your child does better, but it's mostly the seizures, I guess, that respond well. Despite all these things that we learned, of course, there's a lot of unanswered questions that remain. One of them is, for example, what exactly happens in the brain during development in these children? What's the effect of these KCNQ2 variants when the brain is formed in utero? And not only then, is there still an effect on development later? Because if so, if they're after birth, there would still be an effect. This is something that we could act upon. And before birth, it's of course more difficult, but if there's an effect of the variant on development later on, we can maybe tackle this. And it leads, of course, to the most important question for all of you. What is the best treatments, or what can we give our children? Not only to act upon these seizures, because many of you, or many children, will become seizure-free, but how can we target development and improve it? And again, I think this will have to come from teamwork. It's a rare disorder, although many of them, many children will be out there and still be out there and maybe undiagnosed. But we have to put all this information together, and it should come from all over the world. And it needs a help from both patients and parents, from clinicians that treat these patients and can collect information about their story, and researchers that work in the lab with cells and mice and all kinds of models. So we will need international collaborations. And there's many studies in other disorders that have shown that this works. I just give you one example of a recent study that we did. And this is just talking about clinics. It's a study on another gene. It's called, again, one of these letter soups, STXBP1. So it's again a disorder that causes intellectual disability and epilepsy in young patients. It's not an ion channel, but it's a protein that acts in the synapse between two neurons. And we collected, just by reaching out to collaborators, just like we do here, just sending a mail to people we work with, like, hey, do you have patients with mutations in this gene? Let's put them together and see what we can make of it. So this way we collected 45 new patients. Most of them came from Europe, I think 1 or 2 from the outside of Europe in the US. We also collected the data on the 135 reported patients in literature. It's a bit more, I think, than KCNQ2 in literature now, but the disorder has been described, I think, 2008, so it's out there for a bit longer. And by studying them, we could show a bit the different phenotypes. I'm not going to go into detail, just wanted to mention that several of these patients also have Ohtahara syndrome, as some of your kids might have been diagnosed with. Some of them West syndrome, so infantile spasms. And very interestingly, some of these patients have intellectual disability, but they don't have epilepsy. But they do develop, they don't develop well. By doing some statistics, and this is not a very big group, but we could show, and this is something that you would expect when you see that some kids don't have epilepsy but have intellectual disability, that there's no true correlation between the variant type, the seizure onset age or the duration of the seizures, and their developmental outcome, which suggests that it's not the seizures that's the cause of the problems in development in this case, but it's just the mutation, the underlying variant. And why is this important? I think it's important because of things that are also clear in KCNQ2. We don't have to treat or target only the seizures. We really have to target what's going on under the seizures, what's the cause of these seizures and the intellectual disability. And in the meantime, a patient organization has started on this disorder. They started last year, I think. I think they're still very small, but they can definitely learn about from you guys how to build a strong community. So in summary, what do we need? We need to get together, get all this information in one place. And one thing that definitely helps is a registry, a patient registry, and Ed will talk about that later on in more detail. This is the Ricky registry that Ed has put a lot of work in. And what would this lead us? It would learn us. It learns us about the prevalence of the disorder, if we can collect a lot of patients all over the world. It learns us what the mutational spectrum is, which kind of variants lead to KCNQ2 encephalopathy. We can see if there's, or where the recurrent variants are, because as you know, some variants we see in several patients. The eventual aim is also to learn about the natural history. And this is a word that I think yesterday one of the speakers mentioned. If you want to go for a new treatment, if you want to go to the FDA, you need to know what the natural history of your patients is. What is the expected outcome? And we want to know if there's a correlation between the outcome and the mutation or the specific variant. And some patients with specific variants might normally do better than others that are always profoundly delayed. So again, Ed will talk about it in more detail, but this is the Ricky variant or the Ricky database. And you can enter patients in very many different ways. Of course, we extract information from literature. Families can register, or even your treating physician can insert patients, of course, with your consent only. And we bring all these data together just to have it in one place and to learn from it. We don't only want to collect information, but we also want to curate information. And what does this mean? We're going to look with a group of people, and I've been working together with these 4 very nice people. 2 of them are here in the audience. Because we want to learn and we want to be able to predict whether a specific variant in KCNQ2, first of all, whether we can prove or we can predict whether it's pathogenic. Maybe some of you have got a report from the genetic lab saying you carry a variant in KCNQ2, but it's a variant of unknown significance. And of course, this causes a lot of insecurity. You don't know what to expect. So we want to make sure that these variants of unknown significance, that they get some significance. And that we not only can say whether they're pathogenic or not, but we want to be able to predict whether it's a variant that puts you towards the one benign side of the disorder, or it's going to be a variant that leads to the encephalopathy, which might be hard in the beginning, a hard diagnosis, as you definitely all know, but at least you can prepare for the future and you can get the best for your child. So this is the team. The eventual goal, and that's a bit what I said, we want to be able to counsel parents from the very beginning, also because it enables you to start a treatment when there will be a specific treatment in the future. This is for the parents, but of course for researchers it's also very important because it allows us to identify the knowledge gaps, and it allows us to see which variants need to be studied with some priority to increase our knowledge. This is a bit where we stand now. We didn't make any publicity yet for this database because we have been working on it quite intensively lately, but even without publicity, we now have 260 pedigrees. And I say pedigrees because some of them are larger families with this benign phenotype, 160 of which are patients with KCNQ2 encephalopathy. All these patients carry 60 different variants, so this shows that some patients carry the same one. So what I want to do today is to show you that even though we just started this recently, it already has taught us quite a lot. And I'm going to show you just 3 examples. There's more of them out there, but just to illustrate it, the importance. I'm going to talk about 3 different variants of patients that are in the registry. And we start with this one. Again, a lot of letters, and you recognize them from the diagnostic report from the genetic lab probably that you get. There's letters that identify in which place in the protein this particular variant occurs. Now these 2, they were reported in, let's see, in this nice paper from Maurizio Tagliatella, because I told you that last year it was shown that some variants, some rare variants, lead to an increase of opening of the channel, so a gain of function. It's a minority, but it exists. And those 2 particular ones are 2 variants that lead to the, how shall I say, the most opening. So they have a very severe effect on the channel function. And I think Maurizio got this particular variant, or he chose this variant to study, because it also was reported in one of our papers, I think the second paper on KCNQ2 and encephalopathy that we wrote in our lab, in which one of the kids carried this particular variant. And it's a kid from Denmark, so a Danish girl. It had she had seizures from day 1 to day 2. And it was described by the treating physician as bursts of myoclonic erratic seizures. Later on, she developed infantile spasms. And I remember still 2013, I see, that I was a bit surprised that this girl had myoclonic seizures, because most of you and most of your children, probably when they were young, myoclonia, it's a type of seizure, short jerks, like you would have, we all have sometimes when we fall asleep, a short jerk, while most of your children probably they have more tonic seizures. Like they get stiff. So it was a bit surprising, and I actually asked her to go back to the videos and the EEGs to check this, but she said no, it's myoclonic seizure. So that's how we put it in the paper. The child had a profound developmental delay. She was said to have frequent respiratory problems, and she died during her sleep at the age of 2.5 years. So we didn't really think much about this paper, this patient anymore until this paper from Maurizio. So then it started to be clear for us that maybe something else was going on here. And then sometime, I think last year, Sarah Mulkey, another child neurologist, she was here, I think, on Thursday or on Friday. She treated a neonate that also showed very important myoclonic movements that were triggered by touch and sound. So the child started to shiver once you touched it. It had a very impressive EEG, a burst suppression pattern, but she said that there was no correlation between these jerking movements, these myoclonia, and the EEG bursts. So she was not sure these were epileptic myoclonias. So we went to the registry, and in the meantime, we have about 10 patients or 9 patients with a mutation in this exact same position, and we can do a quiz and talk about the flags. I don't know. So this is Denmark. We talked about it before. Somebody know? This is Germany, Holland, Jordany, some US patients, Israel, and Australia. So patients from all over the world. We put them together. We looked at Roberta Chilios. She's not here this year, but she really looked at the EEGs, the video EEGs, together with Sarah. And we now know, looking at these 10 children, that they all have a similar phenotype. They have these neonatal, non-epileptic myoclonies, these shivering movements. Later on, they develop epileptic spasms, or most of them. They're all profoundly delayed. They're hypotonic, and many of them have chronic hypoventilation. They have a lot of respiratory problems. Some of them, they need to be ventilated when they're young and as neonates. um, except for one girl. And one girl, she did not have myoclonus. She only had a mild delay. She developed rather normal, and only at the age of 2 years she developed infantile spasms. And at that time, her development regressed. So it made us wonder what the cause of this different phenotype was. And apparently she carried a mosaic mutation. So what is a mosaic mutation? Every mutation should happen or occur at one time. Now, most of the de novo mutations, they occur when the sperm cell and the egg cell, they get together. The cell should start dividing, and when the mutation happens very early, every body cell would carry this mutation. But when it occurs a bit later, only part of your body cells will carry this specific variant. And this is what happened in this girl. So only part of her body cells, and probably only part of the nerve cells in the brain, carry this specific variant, and she's mildly affected. This, of course, is very important, and it's very important for this particular girl that we picked it up. Because imagine that she would develop well and have children. If she passes on this variant to her child, he probably or she will have this very severe phenotype. So just in summary, by putting data together and collecting patients from all over the world, we can recognize patterns. We knew maybe in 2013 that this patient was a bit different, but at that time, we thought it was an accident. It was by accident. We all are different, you know. But now we know that these myoclonus, which apparently is not epileptic, it's related to this specific variant. So it's a different phenotype. It's a neonatal myoclonus that is not epileptic, so it might need different treatment. And also in general, you might assume that these patients will need a different treatment, but because you could at least theoretically assume that if in these patients that have a channel that's more open than normal, if you give retigabine or ezogabine, that it might have an adverse effect. So this is the first example. I'll show you two other ones. And the first one is this one. Again, this is a flag. It's on a white background. You might know from the names here where they come from. So this is a Japanese patient. It's a paper already, I think it was 2004 or something, so a long time ago. This Japanese group, it describes one single patient with a de novo variant in this variant here, in a girl with benign neonatal seizures. At that time, it was well known. They studied the variant. They showed there was a reduction in M current. So that was it, and the story was finished. But in the meantime, I think we have by now 9 patients with this exactly same variant. Again, you might recognize this one. Denmark, there's Norway, Italy, Israel, US patients, UK, patients from all over the world, and all of them have a more severe phenotype. So this, at first, it was a bit surprising, but this made us wonder, maybe this patient, just as in the other variant that I talked about, maybe this patient is mosaic. So indeed, I think Ed contacted Mr. Hirose here. They looked at the sequencing, and indeed, this girl is mosaic. And exactly this girl, she's developing normal, so she will think about children. So for her, it's very important to have this information. And then a last example, and this is a paper I think that Peter showed yesterday. This one is from 2004, when the group of Peter showed that some de novo KCNQ2 mutations can also be found in families with benign neonatal seizures. And one of these families is this family here. So there's a mom that had neonatal seizures. There's a son with neonatal seizures. This is the Belgian flag, by the way. And both of them, they carry this specific deletion. So there's 3 nucleotides that are deleted. So this means if you have, this is the protein with different amino acids. If you delete one of them, you get a shorter protein. It's still functional, but it doesn't function normal. And this family was reported as a benign neonatal seizure family. At that time, this boy, he was 5 years old, and we knew he had some problems with language. He had some dyspraxia. But again, at that time, we didn't know about KCNQ2 encephalopathy, and we just thought it was unrelated to the variant. And then I think only 3 weeks ago or something, Ed knew about his family through the registry, and he was contacted by a clinician about a patient that that clinician had, who had a deletion. Was it the parent itself? Okay. And he had a deletion only, I think, 3 amino acids further. So it was in the neighborhood. So Ed contacted us and asked us, could you have a look at this family, what his phenotype is like? It's not exactly the same variant, but maybe a variant in the neighborhood that could help this particular family. So we went back and we checked where this family comes from. It's from Antwerp, or in the neighborhood of Antwerp where we work. So I contacted our child neurologist to ask if he still knows this family or he knows how we can contact them. And I said, oh, but this patient, I still follow him. Although now he's, I don't know exactly, I think about 12 years old or so, which is not what you normally see in patients with benign neonatal seizures. They have seizures when they're young and then they grow old, but they're totally normal. They don't visit the neurologist anymore. He says this patient, he really has speech problems. He has a mild delay. There's some learning disabilities. He has some dyspraxia, so he doesn't know how to do and handle things very well. Plus, in the meantime, he has another brother. And this brother, he also had neonatal seizures, and he also has learning disabilities. And he's a bit autistic, so he's definitely not developing normal, and I'm seeing him quite frequently. The mother, on the other hand, she has neonatal seizures, but she's a nurse, and she's doing very, very well. She doesn't have any problems. So this, just to show you that follow-up of families, and this is part of this natural history, is very important. So by following up these families, we see that something is not wrong, not right, that they're developing not totally normal. So again, what we did is we went back to these traces from 2004, these Sanger sequencing traces. I didn't put a picture, I see, but those are those colorful pictures that you often see. And also this mother, she seems to be mosaic. It's something that it's not easily detected with Sanger sequencing, this old technique that we use to still use now and then, to find mutations. But it seems that she, like the other 2 patients that I talked about before, she's mosaic. So this time it's not the child that's mosaic, it's the mother. But she passed on this, for her, benign variant to her children that at this time they present symptoms of KCNQ2 encephalopathy. So in summary, KCNQ2 related disorders are everywhere. It's a global disorder. We don't expect them to be more frequent anywhere else than here in the USA, but still, if you look at both literature, if you look here, if you look at the patient organization, there's definitely a lot of patients missing. Also missing from specific parts of the world. South America, there was a family here, but we don't know about many patients from South America, and there must be more out there. The same from Africa, Asia. There's different explanations for that, of course. First of all, there can be little access to genetic testing. It's a debate here in the US, but it's definitely also the case in many other parts of the world. There might be a language barrier. Some of the families from Europe are here, but even only in Europe alone, there's many different languages, and not all of them speak English. So they won't have access to this patient registry, the organization, the Facebook page. Some families might not have that much internet access, or might not make use of social media and Facebook as others. There might be some cultural barriers, reasons to not share their disorder of their child with the larger community. And definitely there's a lack of advertisement in certain areas in the world. There's several ways to try to solve this. As for the patient organization, what the Dravet Syndrome Foundation does, they have local chapters, mostly in Europe. I don't say this is the best way to go. Translation on the Facebook page or translation on the website might be other solutions, but it's something that we should work on, I think. But there's definitely also a role for clinicians and researchers. We have to promote, we have to spread the word, both in publications, because that's what researchers and clinicians read, but also at conferences. There's the Epilepsy Society, American Epilepsy Society meeting. Each year there's European meetings, etc., etc. And we have to educate our colleagues. We have to stimulate them to ask for genetic testing in children with neonatal seizures, and to adapt our treatment if feasible. So just to make sure that at the end we connect all these children all over the world. And with this last slide, I want to thank you, and I want to thank most of all the patient organization for having us here and making this possible.